Good afternoon, students. Welcome back to my channel, Sir again, to discuss something on nuclear physics. So, this is nuclear low energy reaction. So, low energy reaction means when the particles are moving with non-relativistic speed much less than the speed of light in space. Okay, so these are my credentials, and as you see, I'm going to discuss nuclear low energy reaction topic, and there is a important point in this discussion which is threshold kinetic energy. You will come to know what it is. So in this discussion, we assume that the velocities of nuclear particles are sufficiently small so that we can use non-relativistic kinematics. The classical kinematics we can use. The common nuclear reactions are, let me tell you, between two particles reacting in falling under broadly in three categories. One is elastic scattering. Elastic scattering means the kinetic energy remains conserved. That means the nucleus remains in ground state, because just like the atoms, there are also nuclear quantum energy states. In higher energy state, which is order of MeV, so obviously it is quite a sizable energy. So ground state means it is in the best level of energy state. Nuclear has not been raised to the next ground state, next quantum states. Only difference between the atomic level, the energy states, and the nuclear energy states is the amount of the magnitude of the energy. In atomic energy, the atomic energy states are of EVs, whereas the nuclear energy states are orders of hundreds of kVs or maybe MeVs also. But elastic scattering means nucleus after the reaction remains in the ground state. In elastic scattering, nucleus is left in an excited state and decays by emitting other particles, including photons. So it goes to an excited state and decays by emitting other particles. That includes photons as well, very high energy photons. They can be. The original particle, the third one, the original particle may be observed by the nucleus, and one or more particles are emitted. So this 3 is very common. We are going to discuss the reaction 3, which is very common nuclear reaction. We consider a particle A. A is the particle of mass M, mass M1, moving with a momentum P1 bar and kinetic energy K1 in the laboratory means ground reference frame. Laboratory reference frame means ground reference frame. Like this. Okay. In this reference frame, the target nucleus B, there is a target nucleus toward which the A is moving. Target nucleus mass is M2, is at rest. The most reactions occur with the target nucleus at rest. It means the kinetic energy of the target nucleus K2 is 0 and momentum of target nucleus P2 bar also 0. Okay. We assume that the reaction products are only 2. There can be more, but we assume that only 2. A particle C of mass M3 and the remaining nucleus D of mass M4. Okay. So let the momentum of the particle of mass M3 be P3 bar and kinetic energy K3 in the lab reference frame. Similarly, also let the remaining nucleus of mass M4, that is the, which one? That is the D. remaining nucleus D of mass M4. Let it have the momentum P bar, P4 bar, and kinetic energy K4 in the lab reference frame, the ground reference frame. So the reaction can be represented as like this: B, that is the nucleus, this is the particle striking B, and this is the particle emitted after A gets absorbed, and a new particle from C gets going away, and D is the remaining nucleus. In SUT, we can write like this, and that this means A plus B, A striking B, B is the target nucleus, C is the particle which is coming out, and this D is the remaining nucleus. Q is the energy released in this reaction. We call this Q value of the reaction. We use the energy conservation to calculate Q value for this reaction. So initial energy is equal to final energy. Energy means here mass and energy together. And as long as the V is much less than C, then I can use the rest mass energy plus K1 is the total energy. Otherwise, we have to use the relativistic one. And M2 C square, because K2 is 0. This is the rest mass energy of the that is the target particle, target nucleus M2, which is at rest. I told you that is the after reaction M3 particle comes out, so that is energy M3 C square rest mass energy plus K3, and remaining nucleus M4 C square rest mass energy plus kinetic energy. So if I bring all the M to one side, MC square to one time, so M1 plus M2 minus M3 minus M4 C square is K3 plus K4 minus K1 minus K2 anyway 0 is equal to, this is the Q value. So what is the Q value? The rest that is the difference between the initial particles and the final particles is the Q value. That is also the kinetic energy difference between the final particles and the initial particles. Okay. This is what I given you. A, this is the target nucleus. A is the incoming particle moving with V1. I should put a vector sign V1, and this is mass is M1, particle A, B is at rest. So after this reaction, two other particles are one particle C is forming, and the remaining nucleus D is also will be moving. In this all in the lab reference frame. This is before, so this is after. So this is M3, M4, C and D moving with angle theta 3 with the original line of motion of A. This is the original line of motion. With that, the C makes an angle theta 3 and D makes an angle theta 4. Okay, the momentum of C is P3, momentum of D is P4. Okay, this is what I've shown. This is what happens in that reaction. Before proceeding, I'll discuss the types of nuclear reaction, what will happen in this reaction, what possible Q values. Q can be greater than 1, positive. That means we call it exorgic reaction. Some people say exothermic reaction as well. So reactions convert nuclear energy to the kinetic energy of the products. Okay, means the rest mass of the products will be less than the rest mass of the reactants. So other possibilities, Q is less than 1. Endorgic reaction. Some people say endothermic reaction as well. But the endorgic is more appropriate and exorgic more appropriate. It's not thermal energy is not released in the nuclear reaction. Immediately there is no thermal, it's kinetic energy. Kinetic energy products. Reactions require energy input now. This reaction, the endorgic reaction, they require energy input in the form of kinetic energy of the projectile particle A, that is the incoming particle A towards the target, to be converted to nuclear binding energy. Okay, because this kinetic energy will be converted to nuclear binding energy to form bigger rest masses. In endorgic reaction, bigger rest mass means because C and D will have bigger mass than A and B. A and B together rest mass will be less than C and D together rest mass because this is endorgic reaction. Q is negative. Ma plus Mb minus Mc minus Md C square. If that is has to negative means Mc and Md together will be greater in rest mass compared to Ma and Mb. Okay, this one. If this rest mass is greater than this rest mass and this rest mass, then this rest mass minus this rest mass C square, which is the Q value, will be negative. That's what I have written. 1 is A, 2 is B, 3 is C, 4 is D. Okay. So energy reaction requires energy input in form of kinetic energy of the incoming or striking particle A to be converted to nuclear binding energy. In energetic reactions, we must supply at least enough kinetic energy to the projectile particle A for providing the additional rest mass energy of the reaction products. Is it okay? So in this endorgic reaction, we must supply at least enough kinetic energy to the projectile particle A for providing the additional rest mass energy of the reaction products. Okay. So that means there is a minimum or threshold kinetic energy of A below which reaction will not proceed forward. Means this reaction will not take place. This threshold kinetic energy not only must supply the additional rest mass energy of the products, it has to provide that, but that is not the only thing it has to provide for, but also some kinetic energy of the products, because the law of conservation of linear momentum must be satisfied in the lab reference frame. If it doesn't provide any kinetic energy to the rest mass, if it doesn't provide any kinetic energy to the products, the initial before reaction momentum is there. After reaction, there is no kinetic energy for C and D. Then momentum conservation is falling apart. It's not acceptable. That's why it has to provide for some kinetic energy also to the products to satisfy the conservation of linear momentum. So the minimum kinetic energy of the projectile particle A should be more than what is required to just compensate for the negative Q value. So let's analyze the problem in the center of mass reference. Kyun bhai center of mass reference kyun? Because the linear momentum vector of a closed system of particle is 0 in the center of mass reference frame. You know the center of mass reference frame is 0 momentum reference frame. I have discussed in my previous lectures also. So that it becomes simplified, because the momentum vector is the momentum of a system of particles, closed system of particles in center of mass reference frame is always 0. That's why the name of the center of mass reference frame is also 0 momentum reference frame. So what is the kinetic energy of a two-body system in center of mass reference frame? You must be knowing from basic mechanics. Half into reduced mass into V relative square. So before reaction, what is V relative? V1 only, because V2 0. And what is reduced mass? M1 M2 by M1 plus M2. So that is M2 by M1 plus M2 into half M V1 square means K1. This is the kinetic energy of a two-body system in the center of mass reference frame. That is the before reaction. This is the kinetic energy with respect to center of mass. Remember this important point again. I am emphasizing. It is a non-relativistic case. You are using the classical expression of kinetic energy. The energy consideration in the center of mass system gives you what? This is the kinetic energy before reaction, and the rest mass energy M1 C square plus M2 C square is equal to M3 C square plus M4 C square plus kinetic energy of the products in center of mass reference. Yes, sir, this is energy balance. So this and transfer the C square terms to the left. So M1 plus M2 minus M3 plus it is minus M3 minus M3 and what? Minus M4 C square. I transfer to the left. So this is nothing but your Q value. M1 plus M2 minus M3 minus M4 C square is the Q value. You must be knowing. I just discussed equation 2. So this is equal to this K of products in the center of mass reference. Ke, any whatever reference frame may be, Ke is always greater than equal to 0. The right hand side greater than equal to 0. Left hand side, this is the Q value. And M2 by M1 plus M2 into K1 is plus Q is greater than equal to 0. So as K is, anyway, as I discussed, K is greater than equal to 0 always. So K1 must be equal to minus Q into M1 plus M2 by M2. So K1 minimum must be this greater than this. So and Q is negative. So negative automatically becomes positive. So K1 minimum is K threshold, that is known as K threshold. K1 minimum, incoming projectile particle minimum kinetic energy renamed as threshold kinetic energy is minus Q1 plus into 1 plus M1 by M2. This is for the endorgic reaction only. Okay. This is for endorgic reaction only. I'm writing under this endorgic reaction. I'll overemphasize now. I'll write here that only for endorgic reactions. In red I'll write. Only for endorgic reaction. ओके हो गया ये आपको if m1 is smaller than m2 it is some k threshold if m1 is greater than m2 threshold will be bigger than this much bigger if m1 bigger than m2 yes sir that's what a simple thing to observe एक क्वेश्चन करते हैं भाई find the Q value of the reaction ये proton plus helium 4 gives you this deuterium plus helium 3 ओके ये मास हमने AMU टर्म में मैंने दे दिया चारों का प्रोटॉन का हीलियम का ड्यूटेरियम का and this is the helium 3 का and one AMU is 931.5 approximately मैं AMU में लिखा ओके MEV फाइन सो इक्वेशन 2 यूज करेंगे हम लोग Q वैल्यू के लिए सही आपको अभी बिगिनिंग में बताया इक्वेशन 2 है ये M1 plus M2 minus M3 minus M4 into C square is Q वैल्यू तो फटाफट लगाओ क्या आएगा तो this M1, this M2, this M3, this M4 into C square. I can write this AMU into 931.5 MEV plus MEV by AMU. So MEV term you will get the Q value. So this difference is negative minus 0.0019703. You add and subtract. Take the data. That becomes minus 18.35 MEV. So it's an endorgic reaction. This is the endorgic reaction. Yes or no? This is endorgic reaction. I'll write endorgic reaction. This. Okay. What is the threshold kinetic energy of protons incident on the helium? On the helium at rest? This is the M2, this is M1 having some, they should have some, it's a endorgic reaction. We found that it is an endorgic reaction. So what is the threshold kinetic energy of the striking protons on the static helium? That's what I'm asking. But the threshold kinetic energy, let me put it, that is threshold kinetic energy of protons incident on helium at rest. So what is kth? Minus q1 plus m1 by m2. m1 is proton, m2 is helium. So minus q is how much? Q is already minus 18.35. Minus of that is 1 plus, this is the proton, mu term, this is the helium. I took the ratio almost 0.25, 252 maybe, 1.252 into minus plus 18.35, around 23 MeV. So 23 MeV is the threshold kinetic energy of the incident protons. Quite a big kinetic energy. 23 MeV is not a small MeV for a proton. Understood this? But this is just one of the application I'm discussing. There is nothing much. This is one of the easiest topic I discussed. I wanted to discuss the Q value because my hidden agenda is next discussion will be on Q equation and some application of Q equation. Q equation is extremely important, so important that in nuclear physics that is directly written as Q equation. Okay, so that's why I first wanted to know what is the Q value and what is the endorphic reaction and what is threshold kinetic energy. So these things I wanted to discuss first. I think this is a very simple discussion. All of you might be aware. If you are not aware, by now you must have been aware. Okay, so we don't worry much about this any further. Once you have understood this, don't worry much about it. You know how to handle this. In nuclear physics, only one difficulty is that a lot of accurate calculation has to be done. I don't know how many of you can calculate fast in this type of multiplications and all this. But that is the only thing, complexity in this type of nuclear physics questions in your level. So those who are having good grasp on how to multiply fast and all this, they will have a advantage in this type of questions. So anyway, we don't have much option. So we'll be, because otherwise normally in this question they give options which are very close to each other. So you can't just make some approximation randomly. Yes or no? So we make sure that I don't know, that cannot be helped actually. You have to be slightly fast in doing calculation. Okay. But otherwise, there is no conceptual difficulty involved in this particular discussion. So next question, what I am going to discuss, I told you, Q equation and its application. That is very important for us. Okay, lot of things, some mechanics thing also will be clear there, and here also some mechanics point like what is the kinetic energy with respect to the center of mass for two-body system. This half mu v relative square. Mu is the reduced mass. It should be remembered by you. You should have derived it by now. Must have derived also, I am sure. Okay, and this is the threshold kinetic energy expression. I think I am very clear. So I won't take much time from you now. So very quickly I'll go to the next in line Q equation. For that I made the groundwork today. So thank you all. We'll meet very soon with the next in line discussion. Anyway, those who have not subscribed my channel, please subscribe so that you get the information, get the notification the moment I upload any new videos. So you will be in track. So one thing I can assure you, if you are listening to my video lectures regularly, various conceptual misgivings or conceptual difficulties will be resolved. Thank you all. We'll meet soon.